Well, we're somewhere, I have no idea where we are really, we're somewhere on the Swiss-French border. I don't even know if we're in France or Switzerland. What I do know is that all around us is the Large Hadron Collider. So we're bang in the middle of the ring. So we've got Atlas, which is one of the big detectors, about 4.5 kilometers that way, and we've got CMS, which is the other big detector, about 4.5 kilometers that way. So we're right in the middle of the ring. It's below our feet, all around us. Okay, so the big story is that it was going to create a black hole in the collision. You know, okay, that hasn't happened. Now, there is a possibility that it will create a black hole in the collision. This idea stems from models with extra dimensions that have come out of string theory. Basically, what happens in those models is that the strength of gravity is actually a much stronger force than we previously thought. It just looks weak to us, who's a sort of, if you like, a lower dimensional observer. So the picture is that you have we live on this island universe, which is 4-dimensional, and it's within this sea of extra dimensions. And basically, us islanders have this perception of gravity which is different to reality, and gravity is a much stronger force than we thought. That makes it easier to produce black holes in collisions.
Why?
Well, because what you're doing, think about what you're doing in a collision. You're basically smacking two things together. They've both got a lot of energy, and you're cramming a lot of energy into a very, very small volume. Okay, and you know, there's bounds on how much energy you can collapse into a small volume, because energy and mass are equivalent. So there's bounds on how much mass you can collapse into a small volume before you create a black hole. And of course, if gravity is stronger, then that process becomes easier and more likely to happen. So you could create a black hole.
I completely understand what your explanation about creating a black hole, because we're cramming so much into such a small space. We already get black holes in our universe. They can be created in our island universe, and that didn't require extra dimensions and things like that. I can see how this danger now, but I can't see what the extra dimensions angle.
Okay, so the difference between those sorts of black holes, the astrophysical black holes, and the kind that you might produce the LHC, are that those are very large. They're very large black holes. Okay, they've been formed from stellar collapse. You know, death of a star collapses and forms a black hole, of a star of a certain size at least. The difference between those and the ones at the LHC ones are very much smaller. But the fact that they're smaller is what actually makes them safe. Okay, why we don't need to worry about them. This is if they exist, of course. Because basically, the smaller a black hole is, the hotter it is. So we normally talk about, when we talk about black holes, we say they're black because nothing can escape from them, not even light. But actually, that's not actually true. Something can escape from a black hole, and it's something called Hawking radiation, which was named after Stephen Hawking. It's basically what you get when you apply quantum mechanics to the event horizon of a black hole. You realise that they're not as black as they seem, and that they can give off this type of radiation. The smaller a black hole, the hotter it is, the more of this, the more easily it gives off this radiation. And the LHC black holes will be very, very small, therefore very, very hot. And so they'll evaporate through Hawking radiation very quickly, almost instantaneously. But of course, we've never actually observed Hawking radiation. It's just a theory. It's not something that's been experimentally proven yet, although we do believe it's true. But actually, so that might not be a good reason to sort of allay people's fears. But what we do know is that nature performs LHC-like experiments all the time. Okay, so the Earth is being bombarded by cosmic rays, and in the lifetime of the Earth, we've had about 1 million LHC-like experiments sort of created, essentially, as these cosmic rays at very high energies bombard the Earth and collide with the particles in the Earth, essentially. Nothing weird has happened. Okay, we've had no craziness. The Earth has not disappeared into a black hole. Now, what you could say is, okay, well, the difference between the kind of black hole that might get created in one of those cosmic ray collisions compared to the ones at the LHC is that the LHC ones will be very slow moving, and so they hang around, whereas maybe the cosmic ray ones would just get created but get shot out of the Earth almost immediately. And because of that, you might say, well, okay, so that's not a good reason to allay your fears. But then we look at neutron stars. Neutron stars are very, very dense. Those are getting bombarded by the cosmic rays as well. And they're so dense that any black hole that would be created wouldn't be able to just get away. Okay, it would stay there. And those haven't been swallowed up in the same way. So, because we've got neutron stars, because we're still here, we've got good reason to believe that the LHC is not, very good reason to believe that the LHC is not going to swallow up the Earth.
What would it look like if this area got swallowed up by a black hole?
Okay, so it's it would take a long time. This is one of the other myths. People sort of often believe that it's going to swallow up the Earth in nanoseconds. Let's say hypothetically that all these effects don't apply and that actually it will swallow up the Earth. People say it'll happen in nanoseconds, but that's not true. It would take 10,000 to 100,000 years to actually accrete the whole of the Earth. And the reason is basically because it starts out so small. It starts out so small, and it takes a long time to get to a macroscopic size where it can actually really start to pull things in. So what would we see? Well, basically things would start to get flatter. So not much would happen for, as I said, for about 10,000 years. Things would start to get flatter. All those mountains out there, they'd slowly start to come down, come down, come down. And then eventually, everything would just slowly go down until you had sort of this sphere forming around the black hole, and then eventually everything just collapses into it.
Because I saw a cool YouTube video, and it was like everything was falling down like Niagara Falls. It was
no, cool. It wouldn't be like that. It would be more a case of literally the Earth smoothing out around it, and any structure sort of disappearing. Because one of the key features that we know about black holes is that they have what we say no hair. They have no hair. They have no features. Okay, they're perfectly smooth objects, perfectly round. So the black holes are the sort of the most famous crazy thing that could happen at that people have talked about that could happen at the LHC, but that won't happen. Another one is the idea of strangelets, which is slightly less famous, but also another possible concern that people have talked about. So a strangelet is a bound state of quarks. So these are subatomic particles. So we talk about protons and neutrons. They're made up of quarks. In particular, they're made up of up and down quarks. What a strangelet is, it's a combination of three quarks, up, down, and the strange quark. But it's a lot of them sort of put together to form one sort of large object, if you like, so potentially bigger than the proton.
Like a big quark soup?
If you like, yeah, a big blob of quarks, if you like, yeah, exactly, that's exactly what it's like. You might think, oh, this is going to be very unstable. In particular, the strange quark wants to decay into the up or down quark, so you think this is a very unstable object, but there's something called the Pauli exclusion principle, which says that a fermion, and all these quarks are fermions, can't exist in the same state as an identical fermion. And so having more of these fermions that are different, so up, down, and strange, means that all these fermions can lie in a lower energy state, sort of simultaneously. Okay, so it can actually be more stable even than a nucleus, a conventional nucleus. So what that means is that you have this object, a strangelet, which is potentially more stable than a nucleus. A nucleus are made up of protons and neutrons, which within them have got these quarks. And the other really strange thing about strangelets is that in some cases, if their surface tension exceeds a critical value, they actually become more stable the bigger they get. So you think of putting more quarks onto them, they actually get more stable. Okay, so this is quite worrying, because what would happen then is you get this strangelet created at the LHC, just a little one, but it sees a normal nucleus, and then it's advantageous, it's energetically favourable for that nucleus to be turned into more of a strangelet, for it to combine with that nucleus and create a bigger strangelet, and so on, and so on, and so on, creating ever more strangelets, until eventually the whole world has turned into a strangelet. Now,
dude, turn the thing off! Turn it off!
so there's a theory that this process can turn neutron stars into what's called quark stars, but it's completely hypothetical. It's based on a reasonably exotic theory, but again, we don't think this is going to happen at the LHC, and there's a good reason to believe this. There's another collider in New York called RIC, which is doing similar things to the LHC. It's smashing. One of the things that LHC will do is smash heavy lead ions together. RIC is doing the same thing with gold. And there was the same worries about RIC, that would produce these strangelets. And it hasn't. And actually, one of the things about the LHC is that it's actually doing these things at higher energies. And the thing about quarks is that they don't like to hang around with other quarks as much at higher energies.
Well, I'm not a scaremonger, mate, and I love the LHC, but your sort of defence usually seems to be, it hasn't happened before. Is that good enough?
Well, if we know of events that that are, you know, basically that in nature, like I say, these cosmic ray events are, you know, nature's doing them. We can't control them. Nature's making them happen. And we're like, well, nature's doing it. It hasn't caused anything weird happen. So why do you expect it to happen for us? It's you know, it's a reasonable reason. Look, that guy over there is doing it. Nothing weird happened, so I'm going to have a go at doing it. You could do vacuum decay as well if you want, but probably...
Oh, is this another dangerous thing?
yeah.
All right, go on then.
So there's another possibility is that people have talked about is this idea of vacuum decay, which is, so the universe sort of exists as an excitation about a particular vacuum state. So it's excited, clearly, we've got planets, we've got all this structure around, right? But it's an excitation about a particular vacuum state. There could be other vacuum states. And one of the concerns that people have said is that we could be causing such a large perturbation, a large wiggle in what's going on in this vacuum state that actually we tunnel out of the vacuum state, and that would literally, you know, that would create a bubble of a new universe, sort of where the LHC is. Again, there's these sorts of events going on all over the universe, and you're not seeing these bubbles get created. You know, I said there's about, you know, LHC events have occurred about 1 million times with cosmic rays hitting the Earth. There's, you know, billions of LHC events going on every second with cosmic rays across the universe. So, you know, we really don't have anything to worry about. It's noisy. It's like if you've been on a ship you know, across the English Channel or something, and you're on the hum of the engines constantly. The hadron calorimeter, and then within that you've got the inner detector and the pipe itself. So literally, it's deep within that is where it's all going on, where it's all kicking off.